What's going on, everybody? We've been working for the past couple of videos on calculating confidence intervals, and we've done it on quite a few quantities, population values, temperature, income levels, a wide variety of quantities describing this and that. But there's a special kind of procedure when calculating a confidence interval on something called a proportion. These are percentages of things, proportions of things, fractions of things. There's a specific kind of procedure in doing these kinds of things, and it is the subject of today's video. And so before we get to that, let's take some time for ourselves here to lose our minds and come to our senses, as I might say, to basically clear our mind of thoughts so that we can be completely alert to the present moment. Focus on your breathing. See if you can feel that your body is alive. Take some time to become fully alert in the present moment so that you're fully ready to absorb this new information and take yourself to the next level. Take some time for that. Welcome back. Well, let's first start off by defining some of our terms here. Let's see if we can firm up exactly what we mean by a proportion here. Here are some examples for proportions. As of April 14th, 2020, 0.25%, so 1/4% of the people in Weld County, Colorado, have confirmed cases of COVID-19. That's one thing here. So we've got 1/4% of the people. So that's 1 in 400. Interesting. These are all true, by the way. 12.2% of the people in Weld County are 65 or over. So again, that describes a proportion of the people in Weld County in terms of a percentage here. And then another one, 29.6% of the people in Weld County identify as Hispanic or Latino. This is taken from some of the recent census data. And so proportions can be described in three different formats: decimals, percents, or fractions. And it's a good idea to know pretty fluently how to convert from one to the other here. If we have, for example, 29% here, a proportion listed as a percentage here, like these three are, the way that we convert that from a percent to a decimal, and by the way, this is the way in which we tend to describe proportions in statistics, not as percents, but as decimals, and that involves, the conversion from percent to decimal involves moving the decimal point here 2 spaces to the left. So 29% becomes 0.29 as a decimal. 25.5% becomes 0.255, and 160%, we won't actually be running into this kind of a percent in our investigations here, but it's the same process. We move the decimal point 2 spaces to the left to get 1.6. And in the same way, we can also convert either one of these to a fraction. Probably easier to go from a decimal to a fraction. The way to convert a decimal to a fraction is just to simply think to yourself, what's a way to say this other than 0.29? Well, the rightmost decimal place here is the 10th hundredths place here, so the way that we might say this is 29 hundredths. And in saying that, we've given away what this decimal is like as a fraction, 29 hundredths here. In the same way, we have 0.255, and in this case, the rightmost decimal place here is the 10th hundredths thousandths right here. So this is 255 thousandths, which can actually reduce itself to 51 200ths. Lastly, we have 1.6 here. The rightmost decimal place is the tenths, so this could be, believe it or not, 16 tenths or 1 6/10. Either way, we can reduce that actually to 8/5. So make sure that you are pretty fluent with that and pretty comfortable with the process of going back and forth between percents, decimals, and fractions here. And here is some symbology that we use when we're describing proportions here. A P is used to describe the population proportion. Let's say if we know the exact proportion of people in the country who have blonde hair, we'll say. We'd have to define what blonde hair is. But let's say we know what that proportion is. Maybe it's 25%, maybe 32%, something like that. If it describes the entire population of the United States, we symbolize that with a lowercase p. But most of the time we don't know what the population proportion is. That's what we're trying to find. And so we take a sample of that population and we symbolize that sample proportion with a p, and we have this little sort of caret sitting at the top of it. We call this p hat. That's the way we say this. And so we take a sample and we try to figure out what the population proportion is based upon the sample proportion. Let's say we take a sample of 500 people, a random sample throughout the United States, and we find that 35% of those people that we sampled have blonde hair. Well, that's our point estimate for what the population proportion is. That's our best estimate of what it is. So let's say here we have a population proportion here of 29.6 or 0.296 a decimal portion of the people in Weld County who identify as Hispanic or Latino. Let's say we're not sure what that is. We want to go out and find out what that is. So we randomly sample 20 people, 20 residents of Weld County, and we find that 7 of them identify as Hispanic or Latino. What's our estimate of what this proportion is? Well, it's 7 out of 20, or 0.35. And notice this is an instance in which we would use p hat as our symbology here, because this is the proportion of a sample that we are using to try and estimate or infer what the population proportion is. We can also describe the complement of p hat, that is sort of the opposite here. Instead of taking a look at the 7 people who identified as Hispanic or Latino, 13 people did not identify as Hispanic or Latino, and so we symbolize that with Q. So this is the complement of P here. Notice that when we do this division here, we get 0.65, and these two things should add up to 1. So a good way, easy way to find Q when you know P is to simply subtract P from 1, and you'll find out what Q hat is. And so here are some of the equations which you already witnessed us using here in order to calculate this sample proportion here. The sample proportion here was the number of people who identified as Hispanic or Latino divided by the total number of people who were sampled. In the same way, we used this kind of thing to estimate Q hat here. This is the total number of people sampled minus the people who identified as Hispanic or Latino. So up here, we are getting the total number of people who did not identify as Hispanic or Latino, and if we divide that by n, we get Q hat here. That's the complement of P. And that's the hard way to calculate Q. The easier way to do that would be to simply take P and subtract it from 1 to get Q here. Okay, so let's take an example of this where we're calculating P hat and Q hat here. A random sample of 150 assault victims in a large city found that 45 of them took no self-protection against actions against the criminal. So find P hat and Q hat, where P hat is the proportion of victims. Notice we're dealing with proportions here, not just normal usual numbers here. We're dealing with proportions. Proportions of victims who took no self-protection action against the criminal. Okay, well, what's our best estimate of that? We sampled 150 people, and of them, 45 took no self-protection against the criminal. So it's 45 out of 150, or 0.3. And we can estimate Q hat here by taking the number of people who did file self-protection action against the criminal, divide that by the total number of assault victims, and we get Q hat. So this is kind of the opposite of P, isn't it? And we can calculate it this way, or we could have just subtracted this from 1 to get our answer. All right, so that's how we calculate P hat. That's how we calculate what our estimate is of the population proportion. That's how we calculate our sample proportion. Now let's talk about, once moving out from that point estimate, let's see if we can calculate what the confidence interval is around that estimate here. Here's how we do this. The confidence interval for a particular population proportion is based on the sampling distribution of P hat. Okay, so what we're saying here is that we're going to use the normal distribution. Actually, it's an approximation, but we're going to be using the normal distribution here to describe what we think different instances of finding P hat will be like. Some would be larger than P, some will be less than P, but they're going to be distributed along a normal distribution here. So when the sample size n is no more than 5% of the population size, the sampling distribution of P hat is approximately normal, with a mean of P and a standard deviation of this when Q is equal to 1 minus P. Okay, what are we saying here? What we're saying is that, let's say a bunch of people do these kinds of experiments here where they're trying to figure out what the population proportion is, and let's say it's finding out the percentage of people in Weld County who identify as Hispanic or Latino. And let's see here, the population proportion here, we actually know what this is, 29.6%. Let's say a bunch of people are going out to find out what this is. Well, some people are going to guess pretty close to that, no doubt. Others will guess maybe a little too high. Others will run samples and guess a little too low. But we know, for example, that this is going to, if we plot a histogram of all of the estimates of this proportion over time, they're going to be normally distributed with a mean around the right answer and a standard deviation that is equal to, well, this monstrosity right here, this square root of PQ over N. Now, that notice you have a square root of n down here, which means that this will have the same behavior that we saw with the previous normal distributions, where the larger that sample size is, that means that that distribution gets tighter and tighter and tighter and tighter and tighter and tighter and tighter around the right answer here. So that means that the more samples that we use, that means that the confidence interval is going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller around this correct answer here. And so the way that we calculate a confidence interval once we've got our initial point estimate is to use this, and we're going to be using a z-value as well to figure out what kind of confidence interval base that we're going to have. Is it a 95% confidence interval? We're going to use one value of z. If it's a 90% confidence interval, we're going to use a different value of z, and so on and so forth here. So this is actually going to be very, very much like what we were doing when we were working with the normal distribution, and really even the t-distribution as well in the last two videos. So let me clear the screen here. Okay, to construct a confidence interval around the proportion, you must use the margin of error. Remember, that's the amount that we add to the point estimate, the sample proportion, the sample value of the proportion. So this is what we add and subtract from p hat in order to get our confidence interval here. So the margin of error here is going to be this. Notice, yep, we're using this normal distribution here, and we're using this standard error here. So p hat, q hat, all over n, that's going to be our standard error here. And by the way, in order to make it so that we can use the normal distribution, we have to meet this criteria that the sample size times p hat has to be bigger than 5. That's very easy. That's very common. And the sample size times q hat also has to be greater than 5. That's pretty easy to accomplish. Okay, so here's our value, here's our equation here for the confidence interval. Notice we're figuring out where it's a confidence interval where we're trying to figure out where the population value is. We don't know what that is, so we're estimating it, and we're calculating this confidence interval around where we think this is. All right. And so this is basically how we do it. And we've got that criteria that's listed there. Here's some additional assumptions that are involved with this. First of all, the sample is a random sample. That's pretty standard. You should be pretty aware of that assumption from here at this point. And also, you might recall we have, this is involving a binomial experiment here. And so the conditions of a binomial experiment are satisfied. A fixed number of trials. Each trial has to have only 2 outcomes: yes, no, success, failure. In the relevant group, outside the relevant group, the outcomes are independent of one another. So the for example, if you're sampling for people identifying as Hispanic or Latino, you're assuming that, for example, you are not interviewing 2 people, and the answer of one will tend to influence the answer of the second person if they overhear it. So we're not we're being careful enough in our sampling that that kind of thing is not happening. And lastly, the probabilities of success or failure are constant. So we are keeping that in terms of a constant probability here. All right, so let's try to create this confidence interval here now. A survey conducted by Sally May and Gallup of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. All right, so let's first of all ask the question, what is P? What is the thing that we're trying to find here? In this case, the population proportion here so this is the proportion of students, of all students, paid for their education with student loans. So I'll just say with student loans. And let's also take a look at some of these numbers in here and figure out what role these numbers play. So it's 1,404 respondents here. So that's N, that's your sample size. and you found that 323 students paid for their education by student loans. All right, so that's going to be pretty easy to see what p hat is. It's going to be 323 out of those 1,404. Which means we'll be able to figure out what q hat will be pretty easy. We'll just have to subtract whatever this is from 1. So we've got n, we've got p, we've got q. What's this? Oh, find the 90% confidence interval of the true proportion of students who paid for their education by student loans. Okay, so how do we know what the z value should be here? Well, let's first of all take a moment here. Let me actually put this front and center here. Let's bring back our friendly neighborhood normal distribution here. All right, so this is 0. This is the standard normal here, has a standard deviation of 1. We're wanting to know what the z value is, z and negative z, in which 90% of the data is in between these two z values here. So this is 90% of the data, which means that the remaining portion of the data has to be spread evenly between these two tails here. So we have the remaining 10% spread between here and here. Well, that can only mean that 5% is here and 5% is here. So we want to find a value of z for which 90 plus 5, or 95% of all of the data is to its left. So we want to find z 0.95 from the normal distribution table. So we're going to be using z 0.95 in this process here. So let me clear the screen here. I think it'll be pretty straightforward from here on out. Let's take a look at how we do this here. So again, the sample size is 1404. P hat is equal to 323 divided by 1404. That's 23%. So that's going to be easy to find out what Q hat is. That's 0.77. Both N times P, 1404 times a quarter, that's like 200 and 300 and something. And N times Q, that's like over 1,000. Both of those are greater than 5, so we're fine with using the normal approximation. And we're wanting to use z of 0.95, just like we discovered by drawing that normal distribution picture there. And the z value that has 95% of the data less than it is 1.65. So we just plug this into this compound inequality here, and I'm just plugging things in here to be as explicit as possible here. And what I'm going to do is calculate this portion here. It shows up here, and it also shows up over here, so you only should just calculate it once. And when you first multiply all of these things together, then take the square root of that, and then multiply it by 1.65, what you're going to get here is the margin of error, which is about 0.02. So that's the thing we're going to be adding and subtracting from our point estimate. And what we get is that P is somewhere between 21 and 25. So what does that mean? It means that the true proportion of students who paid for their education by student loans with 90% confidence is somewhere between 21% and 25%. So we've been able to make an estimate about the entire population with some degree of confidence, based, giving this particular confidence interval here. Okay, so give this one a try here. A survey of 6,000 adults found that 58% say they would take a ride in a fully self-driving car. Find the 90% confidence interval of the true proportion who said they would take a ride in a self-driving car. Take some time for that. Welcome back. Well, this involved using very, very much the same skills that we had in the previous problem, where you had to extract some important information out of the problem and apply it to our formula for the confidence interval on P here, which we got right here. So somewhere between 57 and 59%. What is that? It's the true proportion who said that they would take a ride in a self-driving car. So this is a large number of people here that we're talking about. A large number of people everywhere. There's no way we can sample all of them, so we're providing the best estimate that we can with some degree of margin of error here. We know that it's somewhere between 57 and 59%, and we can say that with 90% confidence. There's something I also want to drive home here a bit. This comes from taking our point estimate here. So that's our sample proportion on both sides. And in this case, we are adding something on this side, and we are subtracting something on this side. This is something that we call the margin of error. And we tend to just symbolize it with a capital E here. Just a capital E. So we say that because we use it as a way of describing the size of the confidence interval. You know, how many percent are we talking about here in terms of accuracy or whatever. So, and sometimes that becomes very, very important. If you say, I want to be able to estimate this and estimate it accurately enough that I'm within a certain percent on the confidence interval size. You know, the confidence interval isn't this big. I can only allow it to be this big with a certain amount of confidence. So that's going to be the subject of what we come up to next here. This is where we describe a sample size for proportions. This comes early on in the process of doing an experiment here. Many people think that statisticians only come at the end of an experiment when it's time to analyze the data. That's not true. We're actually with the researchers even in the beginning of the experiment, helping to plan the experiment. And one of the things that we are assigned to do here is to estimate the desired sample size that we want in order to make it so that that normal distribution gets thin enough so that the confidence interval gets small enough to a desired level of precision or accuracy for the estimate here. So how do we do this? Well, you can actually take this formula here and use it to calculate the desired sample size for this. And it comes from what you think. Remember, this is just an estimate at this point because this is before the experiment. What you think p hat is, from that you can guess what q hat is. And here's the desired size for your confidence interval. It's actually half the size of the confidence interval because if you recall, this is where p hat is, and we add e over here to get one side of the confidence interval, and we subtract the same quantity over here to get the other side of the confidence interval. And so when we know what we want e to be, when we know what the size of that confidence interval should be, then we can use e here in this part of the equation. And then it's a question of which kind of confidence interval is this? Is this a 95% confidence interval, a 99? Is it a 99.9? Is it a 90, or whatever it is? And that determines what this is, what our z value is. So it's really just four variables here. Make sure that we square this ratio here of these two numbers, and once we've got that, then we're able to estimate what our sample size should be to get the precision that we want. And of course, let me erase this here. You ask the question, what happens if you get n is equal to 398.2? Okay, so that's the necessary sample size in order to get that confidence interval down to where you want it. You want it to be this or higher. Well, you can't have 0.2 samples at all. Samples are integer values. They're whole numbers. You know, you either do a sample or you don't do a sample. So what this is really saying is that it needs to be greater than or equal to 399 samples. You always, always, always have to round up when you're finding out what n is. And if you know, since this becomes a question here of how do you calculate what P and Q are? You have to give your best guessed estimate of what they are. And sometimes you have some previous studies that you can call upon to give some estimates of these two things. And when you have those, you use that. When you're not sure what they are, what you want to use is a p hat value of 0.5. And that'll mean that your q hat value will also be 0.5. And you might be asking why that is. That's the most conservative estimate. That's basically as bad can get in terms of the number of samples that are necessary. So you're basically planning for anything. So you're ready for anything, if that's the case here. If they're close to the middle, if they're less than 5, if p is less than 5 or greater than 5, then you don't need as many samples here for n. But it's right when it's right in the center here that you need the largest number of samples to estimate it accurately. And so this is kind of a worst case scenario, setting this equal to 0.5 for the number of samples that you're going to need. So it keeps you safe. So here's an example problem here. A researcher wishes to estimate with 95% confidence, okay, that's going to be important, 95% confidence, the proportion of people who did not have a landline phone. Okay, I don't have a landline phone at my house, so I'd be one of those people. A previous study shows that 40% of those interviewed did not have a landline phone. Okay, so we have a previous estimate of this. Proportion of people who did not have a landline phone. A previous study shows that 40% of those interviewed did not have a landline phone. That's our prior estimate for p hat, isn't it? Which means that we also have a prior estimate for q hat. That's got to be 100% minus 40%, or 60%, which is 0.6. Okay, the researcher wishes to be accurate within 2%. Okay, so within 2% here, that's our value for E, and 2% as a decimal is 0.02. We have to find the minimum sample size necessary, and we've got everything here that we need except for the Z value. And so let's once again draw our normal distribution. I always seem to make that x-axis kind of lumpy there. It has a mean of 0, standard deviation of 1, because this is the standard normal distribution here. And we want to find the Z value here. Let's see, 95% confidence interval. We've got a Z value here and a negative Z value. 95% of the data is in between Z and negative Z. That means the remaining 5% is split here and here, split evenly. That means 2.5% here and 2.5% here. So we want to find the Z value here that has 95 plus 2.5, 97.5% of the data to its left. So Z of 0.975 equals what? You have to look that up from our normal distribution table. All right, so let's see how we do this here. So once again, we've got our formula here, p hat q hat, the z value divided by e squared here, and what we found is that z of 0.975 is equal to 1.96. You already knew that though, didn't you? The 95% confidence interval, it has z plus or minus 1.96, so that should be a familiar number there. So that's our value for z here. We divide that by our value of e. Make sure you do this first here and then square it. Order of operations says we have to do exponents first and then multiplication. So after we do this, then do the multiplication, we get 2,304.96. Okay, but what's true about samples? They have to be whole numbers. It's got to be bigger than this. So our minimum sample size is 2,305. We had to round up. We always round up. So you can see we just extracted some information from this problem here, and we calculated the necessary sample size by simply stating the formula, plugging things in, and simplifying and rounding up. All right, so take some time with this problem here. What I did is I showed you the calculation here from the previous slide in an effort to sort of guide you through the process of doing this one here. In the previous study, assume that no previous research was done, so we don't have a value for p hat or q hat. What do? Find the minimum sample size necessary to be accurate within 2% of the true population. The previous calculation has been included for reference. So take some time for this one. Welcome back. Well, this was a problem in which you really didn't have to change very much from the previous problem here. You already knew what the value of z was from the previous problem. That didn't change. You also had the same desired margin of error here from the previous problem of 2%, 0.02. The only thing that changed here is that you had no prior information on what the proportion should be here. And so you had to resort to just using 0.5 and 0.5 here. And you'll notice that the price you pay for that once you put all of this stuff in is the sample size now goes up by a value of about, I want to say 96 samples here, from 2,305 to 2,401. So if you have no idea what the original what any previous findings are for p hat or q hat, then you have to go with this sort of worst case scenario here of 0.5 and 0.5 as far as getting an accurate confidence interval here based upon a certain number of samples. And so more samples are needed when you're not sure what the results are going to be. Okay, so that's essentially what we were doing here. So we've done 3 classes here on confidence intervals. The first one involved using the normal distribution as we were working with things. You use the normal distribution when you do know what the population standard deviation is. You use the t-distribution when you're not sure what the population standard deviation was. That was our second lesson there. And then we had this special lesson here today on proportions, in which we didn't deal at all with knowing what the population standard deviation was for proportions here. We just assumed that we didn't know that at all. But we did assume possibly that you had some previous indications as to what the population proportion is, and you use those in calculating what your desired sample size is. So for today, do you know how to recognize the presence of proportions? We kind of went through and gave some examples of that from Weld County. Presence of proportions, they tend to be between 0 and 100%, or as a decimal from 0 to 1. Do we recognize the symbology to describe these proportions? We used P and Q for populations, P hat and Q hat for samples, and we also defined this thing called E for margin of error. We also used it in our previous videos as well to also describe the margin of error, but we also used it here. And then lastly, recite the assumptions of the normal approximation on a confidence interval for proportions. That was that list of assumptions on that one slide there. It's a binomial experiment, and we have random samples that we're taking. And can we calculate a confidence interval on some of these proportions here? And also calculate a necessary sample size for the proportions here. That was the last couple of problems that we just did. So this is a very, very important set of calculations. You're going to be seeing this in the next few months with the upcoming election here, where we're trying to calculate the population proportion of the number of people who want person X for president versus person Y for president here. So this is the kind of thing that statisticians around the country are going to be trying to estimate as best as they can, and you will see those little margins of error being placed at the bottom of the screen with each one of their estimates, describing really the confidence interval of their estimates here. So what you've gotten from the past 3 days, I think, is going to be very, very significant to you, and I think it's going to be very helpful. So hopefully this is very, very helpful as far as the assignment is concerned, and I'll see you in class.